Hi, I'm Sophia. What are you looking for?
For topological dark matter.
Oh, you should use some clocks.
A clock? Why?
Well, actually, I just finished my Bachelor thesis research on quantum entangling atomic clocks to enhance topological dark matter detection. Are you curious? Let's go. To understand how atomic clocks, topological defects, and quantum mechanics all go together, one needs to understand how atomic clocks work. Every clock is based on a periodically oscillating signal with a fixed frequency, such as a pendulum in a grandfather clock. In an atomic clock, the local oscillator is a laser or microwave source. Since it can fluctuate, it needs to be stabilized. This is why the frequency of the local oscillator gets locked to a transition frequency in atomic systems. If the laser changes frequency, one can therefore detect it with the atoms and adjust the laser accordingly. The uncertainty of an atomic clock is measured by the Allen deviation, sigma y of t. Now, how can we use atomic clocks to detect topological dark matter, and what exactly is it? Dark matter makes up 28% of our universe. Our matter is 5 and dark energy 67. Dark matter is invisible and we don't know what it consists of. One hypothesis is that it is made of very light fields that have formed certain topologies due to symmetry breaking and phase transitions called topological defects such as monopoles, strings, and domain walls. Topological dark matter travels through space at a very high speed and could possibly encounter atomic clocks. What happens when a topological defect interacts with an atomic clock is simple. It changes the energy levels of atoms, which changes their transition frequencies, and in turn changes how the laser gets adjusted, which makes the clock tick differently. The clocks are, however, not good enough. The Allen deviation is not small enough, which brings me to my research, investigating whether the quantum mechanical property entanglement can improve them. What is entanglement? Imagine particles as twins that get entangled through shaking hands. Now, if one twin turns their head, the other one does so instantaneously too, regardless of how much distance is between them. The same thing happens to particles and their quantum states. The idea is now to use the quantum computing formalism to create a model of an atomic clock and entangle the atomic systems. In each clock, there will be n atoms in m subensembles. The subensembles are necessary to find the offset of the laser frequency with high accuracy. Now the clock model undergoes the clock cycle in which the difference between the local oscillator and the transition frequency gets measured. After this sequence, one then needs to estimate the stability or Allen deviation of the clock, sigma y of t. Before we can calculate the Allen deviation, we need to consider other things that can influence our model. One of these things is noise. Noise is the environment obstruting the clock, and it is one of the big opponents of quantum processes. To understand noise, let's use our twins once more. First, they are entangled as before. All information about the position of their heads, their quantum states, is present. Then we turn up the noise. As you can see, due to the noise, the position of their heads, the quantum states changed, and their entanglement even broke. The exact same thing can also happen to the entangled atoms in our clock, which is why we need to apply a so-called noise channel to our model to properly assess the performance of the clock in the presence of dephasing noise. This equation means that with a probability of epsilon, the atomic systems get an additional phase of pi. Once this noise channel is applied, we go through the clock cycle and finally evaluate the stability. For our entangled clocks, its scale is as 1 over square root m times n, which is smaller and thus better than the classical version that scales as 1 over square root n times m. Now, how does the error affect our stability? I modeled an example strontium clock to find out. As this graph shows, once the error probability is below 0.0002, the entangled version of the clock is better by 1 order of magnitude. Given these results, does it make sense to entangle atomic clocks? This is simple. If the error probability is bigger than 0.0002, then no. If it is smaller, however, yes. Now, can we use this entangled clock to detect topological dark matter? The stability range is from 1 times 10 to the minus 17 to 2.5 times 10 to the minus 19. The constraint for the phase difference of a clock due to topological defects is 3 times 10 to the minus 18, which is smaller than the maximal stability, meaning we could possibly detect them. From this phase difference phi, we can estimate what kind of topological defects we could find. Our model is the blue graph, meaning we could detect dark matter up to a size of 10 kilometers and an energy scale of 10 to the 9 tera-electron-volt. The other two lines show smaller ranges set by previous research. This, however, does not mean that we can detect them. Our constraint is an upper limit on the value, which is very limited by the stability of the clocks that were used in prior research. We just don't know how big the influence of topological dark matter is on normal matter, which means we can't say for certain that an extra order of magnitude will suffice to find topological dark matter. One could, however, use these improved clocks for other use cases, such as gravimetric missions. These detect differences of the gravitational potential with atomic clocks on satellites, using the fact that gravity warps space and time. An example is the GRACE mission, which measured essential climate variables such as melting glaciers or rising sea levels. It is also important to consider the ethical implications of this project. Since this was a theoretical physics research, there are no conflicts with data security, privacy, and so on. It is, however, important to ask, does it make sense to spend resources and time on this topic? Since there are use cases that are very valuable to society, such as investigating essential climate variables, it is a worthwhile project to do. Overall, entangling clocks is a good approach as long as the error issue gets fixed. Can we use them to detect topological defects? That is uncertain. But since it has other use cases, it is a successful research project.